Vi testar, det fungerar. Okay, good morning. Good morning to you here in the room and good morning to you online. And welcome to this very first Ocean Breakfast Seminar. Today we have an exciting presentation about unexpected methane emissions that are triggered by ship passages. But before we go on to the presentation, I would like to take the opportunity to say a few words about our thematic area, Chalmers Ocean. My name is Ida-Maja Hasselöv, and I'm the thematic leader of this area. And I'm from the Department of Mechanics and Maritime Sciences, where we carry out a lot of both research and education related to shipping and offshore energy. Other departments at Chalmers that have a lot of marine or maritime-related activities include LIFE, where we have a focus on seafood and the blue bioeconomy, for example. At the Space Earth Environment Department, a lot on remote sensing, for example on ship ice drifting, and or sea ice drifting, and sulfur oxide emissions, for example. At the Department of Technology, Management and Economics, there is a long track record of cumulative impact assessment and marine spatial planning. And also at the Department Architecture and Civil Engineering, we find a lot of activities on shipwreck risk assessment or remediation of contaminated port sediments. So to conclude, if we scratch a little bit beneath the surface, we see that we have marine or maritime-related activities at all Chalmers 13 departments. And with the thematic area Chalmers Ocean, we would like to facilitate Chalmers' contribution to solve or address the grand challenges that we face linked to the marine environment. And we strongly believe that to turn the negative trend that we see in the marine environment, there is an urgent need also for other disciplines than the traditional marine sciences. And we are now halfway through the UN Ocean Decade for Sustainable Development. And we hope that Chalmers Ocean can be a node internally and externally to facilitate our contribution. So if you are interested and want to know more, please don't hesitate to contact us. Now I will introduce the speakers for today. We have Johan Mellqvist, professor in remote sensing. We have Amanda Nylund with a PhD in maritime environmental science, and Rickard Bensow, professor in hydrodynamics. So I leave the word to you, Johan.
Okay, I speak here, and you go there. Are you're really far away? You can come closer. Okay, so this work is it's really good example of this interdisciplinary work, or what you could call it. We are very focused on ship emissions from the exhaust. So long time ago, 15 years ago, we measured ship exhaust from St. Petersburg, and after we saw the exhaust, we saw this strange tails of methane. We saw a lot of methane. That was not from the exhaust pipe, apparently. So it was somewhere from the water. So it's like, and we were there several years, and collected data, but it was not we were not paid to do that. So it ended up in the data library, data graveyard that I have. And then I met Amanda on a workshop, maybe 5, 6, 8 years later, I don't know when. And then she told me about she was doing these effects of ship turbulence and so on, how ships affects. So then I said, I have this data. Can you not have a look at that, And so on. And that's why we are here now today. So eventually, we even wrote a paper. Amanda wrote a paper, or we wrote it together. So today I'll talk a little about our measurements that we have done, the ship emission measurements. And then Rickard will talk about the ship-induced turbulence, and then Amanda will basically tell you about the results and how we looked at this methane. And there's a paper that you can look at that if you're interested. Yes, so at Chalmers, we have had a lot of focus on trying to measure ship exhaust, and it's driven basically by that there was the ships cannot have, there's a limit on how much sulfur they have in their fuel. In the IMO, they have this Annex 6, which tells you that here now they have to have less than 0.1% sulfur in the fuel. While worldwide you could have up to 4.5%, and that has decreased now to 0.5. So we have worked a lot with techniques that can monitor ships remotely in the ship plume to figure out how much sulfur is there in the plume, and to see, you know, if they fulfill the IMO regulation. And also we've done work on NOx and particulates and etc. So I will tell you a little about that. Take the opportunity. So as I told you, we had a project in the Baltic Sea regional project, BSR, Innership it was called. And where we actually were parked in this, we had a boat that we had some equipment on, and we measured ship exhaust from ships going in the ship lane on the Neva Bay, which is a sort of inland sea close to St. Petersburg. And we were like parked downwind of the ships a couple of 100 meters, and then we got the ship plumes that we analyzed. Yeah, and one example is this is black carbon. So this is the gram black carbon per kilo of fuel, divided into different type of ship categories here. Normally you would expect that below 1 here, as you see that many of the ships are. I mean, you can see that these service ships, they stick out. It's these service ships that take oil from St. Petersburg to Ustluga and so on. So that was like an example of a result, and this is in a paper. Also, we looked at the fuel sulfur content. You can see here that there was actually a limit at 1% limit, and this is a histogram showing number of ships and the sulfur fuel content. So we could see here that about 20% of the ships were not complying. Can you please start here? So just an illustration how we do measurements. You can either do it from aircraft, from a parked ship or a moving ship, a measurement vessel, or it can be done in a fixed way. There's supposed to be a bridge coming up here. Yeah. So we are doing this measurement at the Great Belt Bridge and the Öresund Bridge now, operationally for the transport agency, Transportstyrelsen, who are yeah. And this is another example of measurements at the Great Belt, where we have this, where we can calculate with the ship plumes how they travel, and we can correlate that with the concentration values that we measure from our sensors. And you can see that when CO2 and SO2 and NOx they sort of correlate, you basically calculate the ratios of sulfur to CO2, which is the sulfur to carbon ratio in the fuel. And from this you can get gram pollutant per gram fuel. Okay, and one example here which relates to methane, but it doesn't relate to St. Petersburg. And it's something that we are studying. That is the LNG ships, ships carrying LNG. They run on methane. And you can actually see very high slips from them. They can, up to 12% of the fuel can be just unburned, not on average, but like so between 0 to 12. So we are right now in the process of writing a paper, putting together these 500 measurements that we have done at the Great Belt Bridge. You can see here methane and CO2, how they correlate at the bridge. And methane is, as you probably know, 20 to 80 times stronger of a climate gas, depending on the time frame that you're looking at. So that's so all the releases will always be multiplied by some type of factor to get it to climate effect. In St. Petersburg, we detected these plumes, as I told you about. I don't know how visible it is, but here's a ship exhaust, and just behind there is this plume of methane. You can see they are equally strong, these plumes. I don't know if you can. Does anyone see it? You do see it. And that told us it's not coming from the exhaust. It's coming from something else, and this is why we are here. We also did some complementary measurements of methane in the water and putting floating chambers and so on, showing there is methane in the water, but we didn't have a good explanation at the time. And the way we did the measurements is basically we first calculated based on the ship exhaust measurements. We calculated how much we had a model calculating how much fuel the ship was using. And then we measured the ratio of methane and CO2 from the ship, assuming a similar distribution with some corrections. And from this we could get the emission of methane in gram per second from what we actually looked at. So this is the type of data that Amanda has been analyzing. Okay.
So, as Johan said, this plume of methane came behind the vessel. What piqued our curiosity was then what is actually causing this. So we needed to figure out how the ship is affecting the environment around, and not just the ship. So in naval architecture, when we design ships, build ships, we look at primarily the performance of the ship to make it as fuel efficient and as safe as possible. And then we look, in ideal conditions, we look at deep sea and calm water, where we have contract conditions for the ship owner and the shipyard to agree. And we look at the local effects. So what's the power consumption that this vessel has when it runs? So this was a bit unusual in these questions then, because we had shallow water, we had in the bay and the fairway, and it was behind the ship. So we needed to look in the far wake, or at least much further behind than what we do in our normal usage of our ship assessment. So in this case, if we have the ship here, we normally only look at the propeller and hull, say, but now we also wanted to look a little bit in the wake, a couple of ship lengths behind. And what happens here, we had already started working with Amanda and Ida Maya and the others on this. So you have a spread of pollutants, you have a mixing, so the propeller rotates and swirls the wake. And then you can look at how this interacts with the stratification and other things. And right now we also have a project where we're going to look at microplastics, how that is released from the ship and spread into the ship wake. So we had started looking at this a little bit. And from what we saw from Johan's measurements, we needed information in the wake, maybe 20-30 seconds behind the ship. And as Amanda also will tell a little bit about, then you can't really measure the details this close around the ship. So we needed to use computer simulations in some way to assess what's going on. And we also needed the flow motions, because we thought this had to do with mixing in some way. So the standard design methods are not sufficient. So we choose a CFD approach where we can resolve the wake, the structures, and we also had a moving propeller or propellers in one of the vessels, which means that these simulations are very expensive. So we're talking about 3 to 4 weeks on a computer cluster for one case. And here also you can see one of the vessels, Ropax, a ferry, and we modeled the sea bottom to confine the domain to get it as close as similar as possible to the case. So we had to pick a little bit. We couldn't check all the vessels that were monitored, so we picked 2 cases, a medium tanker, which we believed had little methane induced release, and 1 RoPax ferry that was larger and more regularly could be detected methane from the measurements. And this was also a bit of a problem digging out these, because ship geometries are generally not available. So we couldn't just contact the ship owner and get the geometry. So we had to dig a little bit in our drawers to find something that we could use. And here's just an example of what we get from the mixing. Amanda will talk more about this. But here we see the turbulent dissipation rate, which is an indication of small-scale flow structures in the wake. So we have here the tanker and the wake about 1 ship length behind, a little bit more here. In the horizontal plane, just close to the surface, and here we have the depth. Here's the bottom of the passage. And we can also compare with the RoPax ferry here, which have a little bit different character, different depth. And with that, I leave to Amanda.
Yes. So my part of this was mostly focused on the part of the wake that Rickard didn't model. I've been working a lot with trying to use field observations of different types to study the turbulent wake and its effects. And as Rickard said, it's very difficult to measure just behind the ship in the turbulent wake. So that's where modeling is necessary. But now so why is it important to understand the turbulent wake? As mentioned before, everything that's discharged from the vessel will end up in the wake, and the wake will determine how these pollutants are spread and where they end up and how they get diluted. But in addition to that, we also have the effect of the bubbles and turbulence on air-sea gas exchange. So that's the physical disturbance itself will affect how, for example, methane can be released to the atmosphere. So in this paper, this work we did together, we found some interesting results. This mystery of these methane plumes, we found that the combination of pressure change from the passage of the ship and the turbulence in the ship wake causes the release and ventilation of methane from the sediment and water to the atmosphere. So in the study area of the Neva Bay, we have made measurements in this area. So all the results I present now are confined to this stretch here, but the conditions are quite similar along the entire shipping lane here. We found that in this area, you have an estimated release of 120 kilos of methane per day. So if you don't know a lot about how much methane is usually released, this was 20 times higher than the ambient emission from the undisturbed areas. And also, which is maybe even more interesting, is that even though this area is very small compared to the entire Neva Bay, it corresponds to 15% of the total emission from the area. So even a small area can contribute quite a lot to a local emission. If we look at the different types of ship we studied, 28% of the ships in the data set triggered emissions. Then it's important to consider that a lot of the ships in this data set were designed to go on the Neva River. So they were river vessels with a very shallow draft. And these ships did not trigger emissions. So of the more regular-sized commercial vessels, which we have here in this figure, you have the different ship types on the x-axis and the magnitude of the emission on the y-axis. We had a much higher percentage of triggered emissions. So for example, container ships and cruise ships triggered emissions more than 75% of the time. And these emissions, on average, corresponded to a 22 increase of emissions of carbon dioxide equivalents compared to the exhaust from the fuel. So when we looked at this data set, we could clearly see that there seems to be a difference between different ship types. And we wanted to try to look into the potential governing factors. So can we say what type of ship or what type of parameter that is governing how much or how often methane emission is triggered? So we started with pressure, since it's known that pressure changes can trigger methane emissions from sediments. And we could clearly see that if you have higher pressure-induced change from the ship passage, it's a higher likelihood that you will have trigger methane emissions. So the blue dots indicate methane emission, and the orange dots indicate that there is no emission. The pressure change is affected by the speed and size of the ship. But we also looked into the size and speed separately. So we could see also that the ship draft seemed to have an effect. But you also have ships with a very large draft that still didn't trigger any emissions. So it wasn't as simple as that. Then we looked at the length of the ship. Here it's interesting to know all these river-going vessels were usually 125 meters, so they never triggered any emissions. But above that, you could find ships triggering, but still you could have very long ships that didn't trigger any emissions. And the same goes for speed. Here you can see a clear correlation that you need a higher speed to trigger an emission. But you can still have a fast boat that triggered no emissions. So we know more, but there are still a lot of question marks. Another parameter we looked into is related to these different ships that we modeled. So the Ropax ferry that Rickard mentioned is similar to the one you see up there in the corner, or similar to the Stena vessels you have here out on the river. And as Rickard said, it has two propellers. So we wanted to have one ship type with two propellers and one with one to see if this could have a difference. And what we could see then is that the Ropax ferries have intense turbulence field that can reach down to the sea floor in the area where we studied, which was about 14 meters. We also have made field measurements where we've seen that these types of ship can have wakes reaching down to 30 meters, so that was no surprise. The other ship was a small tanker or medium tanker, so it's not the tanker here in the data set, because these tankers never triggered any emissions. So it's a smaller tanker that, looking like this, and there you can clearly see that the turbulence field behind the ship is much smaller, also the pressure field. So, but what's important, so we thought maybe it's the twin propellers. But then if you look at these main suspects here, the cruise ship, Ropax and Ro-Ro vessels have twin screw propellers, but the container ship doesn't, and they had the largest emissions and most frequent. So there is still more to look into here. So if we look a bit further ahead, considering what we do know is that we have found this ship-triggered emission of methane, and we have started to understand the processes triggering it, which means that if you have an area where you have a lot of methane in the sediment, and you have ships passing, and the water is shallow enough for the pressure and turbulence to affect the sediment, then you can trigger these emissions. And if you look at these figures, this one up in the corner is the ship traffic density globally. And these other two here show hotspots of where you have a lot of methane in the sediment. So as you can see, there are a lot of areas, like shallow coastal areas with harbors, in areas where these two overlap. So what we can say is that it's very likely that this happens elsewhere. But to know the magnitude, you need to go out and measure, because how much methane that's being released is very dependent on local hydrography. But there are a lot of more interesting places to go and measure. It's also interesting to look at the temporal aspects, because the measurements that Johan and his group made were only made in summer. So depending on where you are, that's also an aspect that needs to be considered. And then finally, some concluding remarks. So compared to the emissions that Johan talked about from the LNG vessels, where you have a methane slip, where you have specific ships that emit this wherever they go, here you have all ships that can trigger these emissions, but in a confined area. So it's a slightly different way to estimate these emissions, and they are not easily directly correlated, even though it's the same gas that's emitted. The mode they are emitted are a bit different. Regarding potential mitigations, can we do something about this? I mean, we clearly saw that the small and slow vessels didn't trigger emissions, but these vessels are much smaller than the ones you would use for commercial shipping. So as long as we don't use river vessels on the open oceans, we will continue to have this issue in ports or shallow areas. So the only thing we could really do is decrease the need for ships and the number of ships to mitigate this emission. Another interesting question that we need to consider is then, okay, now we know this is happening. It's happening frequent enough to know we should consider this, but how do we account for it? It's not related to anything that the ships consume or bring on board. It's related to a natural process that's being altered or disturbed. So how do you regulate this, and who is going to be accountable? And finally, I would like to once again come back to the kind of interesting start of this project. These emissions were discovered by chance, because someone, or Johan and his friends, were out measuring in a shipping lane. And we wouldn't have known about these emissions if they haven't been out there. And shipping lanes are seldom included in monitoring efforts, because it's very difficult to measure there. I know, it's hard. It's also considered a disturbed area, and you want to know the undisturbed or the natural situation. But as we can see, even though the shipping lane is a very small area, it can still contribute to a large amount of the total emissions. So we need to start looking into the shipping lanes. There might be other things there that we still don't know about. And then would also like to say that this project will continue, so hopefully we'll have more interesting results in the future. So, and we would like to thank all our collaborators. Not everyone was here today, but it was a collaboration between Chalmers and SMHI and the Finnish Meteorological Institute. So, thank you.
Thank you very much. I am, of course, a bit biased, thinking that this is super interesting and looking forward to this new project. We are currently recruiting a new PhD student. Amanda, you touched upon it a little bit in your final or concluding remarks, but you mentioned that it's very difficult to sample in a shipping lane. Would you like to elaborate a little bit about that for people that maybe haven't been near a shipping lane?
Yes. Well, so first, it's important to consider the scale of the ships we're talking about. So we're talking about large commercial vessels that can be several hundred meters long and very large. So the turbulent wake behind that ship is very turbulent. And you're not allowed to get, it's very difficult and maybe not even allowed to get really close to the vessel. So apart from the practical challenges of getting there in time to do measurements, then you also need to have instruments that can, that you dare to put down in this very turbulent environment close to a vessel. So many of the type of instruments used today to at least look at the impacts of this type of turbulence. Maybe if you want to measure temperature and salinity or understand how it looks in a profile, you need to actually put an instrument in the water. And these wakes are they can sustain for up to 10 minutes, but the most turbulent part is in the very beginning. So if you don't get there in time, you will miss that part of the wake. So that's where we actually needed the modeling from Rickard, because we had this time gap of maybe 30 seconds up to a minute, which we couldn't measure. So we do have used some remote or type of remote measurements using acoustic instruments, where you don't have to have in the wake, you can put it below it, and then it can measure the water column above. But there are a lot of challenges, so it's not arbitrary to go out and measure in the wake.
Thanks a lot, and I agree. Are there any questions from the audience? Please say your name. And
hello, Jana Moldanova. This was really super interesting. I wonder one thing, when you talk about this release of methane from the sediment, have you been looking into what's the biogeochemical cycling of this sediment? Is it like accumulating, so it would, because you said there are small, low emissions, so I just wonder if it's like, you know, you shake it up and get released, otherwise it would slowly seep out, or if it would be buried, so this is actually a source in a longer term.
That's a very good question that we have been thinking a lot about. So in this project, we did not do methane measurements in the water column. So we can just infer from what we know. What we know is that there is from other studies, we know that there is a high biogenic production of methane in the sediment. It's an area where you have a lot of organic material accumulating, and you have, there is methane production in the sediment. There is also a relatively, if you compare with the rest of the Baltic Sea, you have a high content of methane in the water. So the flux is already quite high. Regarding if this would have been buried or released anyways, so what we do know is that these measurements were done for quite a long period of time. So you will be out for like 24 hours in a row measuring continuously. So what we can see is that these type of emissions that we see after ship passage do not occur in between. So these large emissions, or like increase emissions of methane over time or during certain meteorological conditions, etc., were not observed in our measurements, which were made during 2 consecutive years for several days and weeks. So based on what we know, at least during the summer period when we were measuring, this methane would likely not have been emitted in this amount if the ships had not done it. We could also see that there have been studies before looking at how waves can trigger methane emissions, where it was, but this in a lake, where it was reported that after a while the kind of methane ran out. But we could not see that. It was almost the opposite. It was not, we didn't have enough data to do a good statistical analysis, but it was rather that we could see the more ships, the more methane. So we couldn't see that the methane ran out. So in that sense, I mean, we are quite confident to say that even at least during the period we measured, there would have been less methane released if there hadn't been any ships. But you would need to look into the specific biogeochemical and like processes, or if it's like released as bubbles or very high methane content, you would need to do measurements in the water as well. Yeah.
But a comment is that the $1 million question here is, would this methane still go out? You know, but it's like, at least in our paper, in our hypothesis, we say it's shaking the bottom. It's something that it's in the mud, you know. So it's definitely increasing it's increasing the travel time. Well, it's shortening the travel time for the methane. I mean, it's being produced, and then and once in the water column, it's actually quite quick. So there's more chance for this bacteria that can consume the methane to do it if it's on the bottom. And we did do some oxygen measurements, and there were actually oxygen on the bottom for some reason. We were kind of surprised, which means that there could also be this bacteria. So, but that's another study. You could say we don't have the answer, but it's definitely it's increasing, it's lowering the time, travel time. So there is an impact, but if it's the full impact of these 22% or not, that we don't know. I mean, it will be less, of course.
Thank you very much. Did we have another question here?
I was just wondering if lowering the allowed speed of even the big ships, would that lower the emission also if it decreased the speed?
So we could see actually, like over 10 knots, it was much more likely to trigger an emission. So lower speed would probably help. It doesn't remove it. So this is also, I often get the question, like, I know I mentioned during presentation, like shallow enough or fast enough or slow enough. And I say that because it depends, like how fast or big the ship needs to be depends on how shallow it is, because the pressure change and the turbulence depends on how deep it is. So one could, so we haven't, yeah, so slow, I mean, it will not be more emissions if the ships go slower. No, so that would be one thing to start with. Yeah, but it's still, this is still an area where you have speed limitations since it's very near shore and shallow, so they're still going quite slow. So, yeah, but that's a good question.
I mean, it's still a limited data set. So you could argue that why did we not do multivariate? Why did we not fit all these things at the same time and so on? But it's not, the data is not, it's not enough data basically. So we had to take one parameter at a time, and then the disk pressure effect was the most significant. The other ones, they were like, it's kind of inconsistent, because I mean, length and draught and pressure and all that, they are, of course, they are dependent. They correlate. They are not independent things. So you would have to do a multivariate. If you had more data, we could have done a more rigid analysis.
Thanks a lot. Are there any other questions from the audience? There was one.
Hi, Johan Mellqvist from RISE. I was just interested in knowing if you're planning to look at the depth, doing any different modelings for different depths, like at what point does it get deep enough that these emissions disappear? Will that be modelled or measured? And also about looking at in a different sea area, for example, outside of Gothenburg, if there's the same type of sediments there or if it's deep enough. Very interesting work, though. Thank you very much.
Thank you. I will begin answer and then you can pitch in. Well, regarding to, I will start in the other end because then I think I will get to the answer. So there are a lot of other areas that will be of interest, especially the big, river deltas. So many of the big harbors in both the Baltic Sea and the North Sea are at the mouth of big river deltas, where it's has been observed that there are lots of large methane contents. So it will be interesting to measure somewhere where you have more of a depth gradient. So the Neva Bay is very special because the surrounding water, apart from the shipping lane, is like 5 meters deep, and you have a dredge channel that's like the same depth everywhere. So you can't really do look into the impact of depth like in the field. What we have seen before is that our field observations of the wake turbulence and the modeling is not a perfect correlation. We don't understand everything yet to model it perfectly. So to do it at this stage we are now, I think we would need to do measurements in an area where you have different depth, and then we could also look at it mathematically or model it. But there are a lot of areas both in Europe but also in Southeast Asia where you have ideal conditions for this process to occur. So it would be very interesting to measure there.
But I can complement that it would be possible to look at this a little bit more and change the parameters. The simulations I did now were to sort of investigate and try to figure out what happens. So if we now think it's these parameters as water depth and ship speed, or clearance perhaps between ship and bottom, then one could probably use a little bit less costly methods to span that parameter range a little bit more. But we didn't have time to look at this in this study. But it could well be that if you dredged a little bit deeper, then you would reduce the problem as well.
Thanks a lot. And for our listeners that maybe are not that well versed with ship hydrodynamic modeling, you just mentioned that it would be possible to use some less costly methods, if I heard it correctly. Would you like to expand a little bit upon that, and maybe also say something about our challenges? We heard about the challenges of doing the sampling, but also the modeling, I guess, was a bit challenging with respect to time and so on.
Yes, so in this case, since we wanted the wake behind the ship, that's really what is costly. So we needed to have large resources to compute the flow structures in that wake, and for a long period of time then, 30 seconds, which is long in our world. When a propeller revolution, normally maybe you can run just a few, and that takes, then you have sort of 2 revolutions per second. So this is maybe 20 times longer than we usually need to run or so. So if we don't need that far awake, we could maybe do one case in, or maybe even 2 cases a day or something on more limited resources.
Exactly, that was new experience for me as well in our collaboration. And I recall when Amanda and I asked if you maybe could model like half an hour or so, and then now we are extremely happy with 30 seconds. But still, there were weeks for the computing time. Yes. Okay, thanks a lot. I realized that I don't know if we have any questions online. Robert, do we have any? Okay. And no other question in the room. There are plenty with breakfast still, so I hope that you take the chance to stay a few more minutes and take the chance to talk with us about this study or other topics. And yes, please, Amanda. We are planning for a follow-up on October 17th. The topic will be related to our research in the polar areas. So please join us next time, and until then, have a good time. Thank you. Bye. Thank you.